Hey, today's episode is about a startup named Quilter that aims to accelerate global innovation in electronics. The goal is to build a system analogous to a compiler that can help automate circuit board design. As you might expect, this is a really hard problem. So I spoke with the founder and CEO Sergiy Nesterenko to understand the problem landscape and how he thinks about negotiating difficulties and delivering a product customers might want. This is the Gradient Podcast. I'm Daniel Bashir. The best way you can help me out with this project is by sharing it with people you know and by leaving ratings and feedback. And now, Sergiy Nesterenko. One thing I noticed about the Quilter homepage is that there's a very succinct two-paragraph description of how Quilter kind of came to be in its current form, which is this clean version of you designed your first PCB at SpaceX in 2014, and you realized that computers could kind of do this, and that was a rate-limiting step for people. And then Quilter kind of came about. But I do think you've talked elsewhere about how it's maybe not as clean of a story as those two paragraphs would tell us, and there was some pivoting involved. So I'm wondering if we can maybe start with what's missing from those two paragraphs.
Yeah, gladly. So there's really a lot of time between when I started thinking about automation for PCB and when we decided to do it. So, the story is true that, I started at SpaceX in 2014. One of my first tasks as an intern was to design a board, tried to use automation. Automation failed me, spent weeks designing that board. And then that board actually caught fire in my hands when I first brought it up. Not a fun experience. And that was despite reviews from, more senior engineers who knew more than I did about designing boards. And we all missed a bunch of really obvious things in retrospect. I kind of just, for the whole time I was at SpaceX, the 5 years there, I just kind of took it as fact that okay, we design boards by hand. It is what it is. It's rate limiting, but I'm not going to really question it. So I left SpaceX and, I would do contracts on the side and I ended up contracting with an investor who was I was helping him do diligence on another company. And in that process, he kind of turned around and was like, "Hey, would you like to start a company?" And I was caught off guard and said, "What? Really? Okay." And so I jumped into starting a company without really here's an idea, here's a path forward, here's an MVP, here's a deck even, right? And so I kind of acknowledged in that first year that that very fortuitous, but not how it's supposed to happen. And so I put the investment in kind of a hibernate mode, and I kind of faced the fact that I have to actually go and explore what it is exactly we're going to do. So, we started off with this notion that, maybe we can make low-cost sensors and started making some basic prototypes, talking to people about it, realized basically we were too late to that party. Then started thinking about doing kind of anomaly detection and data processing on that kind of stuff. Ended up getting the interest of some big companies, but they ended up offering me jobs rather than contracts. And so realized that wasn't going to work either. Then I started thinking about anomaly detection in build PCBs. Kind of learned more about optical inspection of what already exists. That seemed kind of good enough. Then I thought about detecting anomalies in the design, of this hey, why don't we take a designed board and find things that would have caught the board on fire, right? From SpaceX, I had the experience of being in a job where I tell other people that they didn't do their job well. And I didn't like that experience. And I thought, okay, well, why don't I just design it correctly in the first place? So finally, we ended up in this idea of why don't we just actually design PCBs from scratch and then take into account all the physics and all the things that we were going to detect, rather just do them correctly in the first place. A much longer journey than two paragraphs, but that's maybe a bit much for a landing page.
I wanted to ask you about two things that came up earlier in your answer. And one of them was about the fact that even after senior engineers reviewed some of your design, it seemed like everybody missed things. And I'm aware that in general, there are kind of standards for doing design reviews for these sorts of things that people tend to look for. I'm wondering, I suppose Elon's companies are known to value speed as a really key thing that they focus on. So I guess I was maybe wondering, as you said that, whether you felt like this was a SpaceX specific thing, or having spoken to other engineers, interns who maybe have gone through similar design reviews, if that's something pretty broad.
It's definitely pretty broad. The so you know, of course, SpaceX values speed. You know, on this particular project, it wasn't like a critical path project. You know, it's my first intern project after all. So time pressure wasn't really the issue. The issue is that in general, like for any electrical engineer, if I just show you a circuit board design, like a layout, right? So you're looking at the outline of the board, where all the chips are, how all the traces are connected, so on and so forth. It's actually very, very difficult to know if that design is going to work. So even forgetting about mistakes you might have made in the circuit schematic, where you kind of logically described how the chips should connect and what functions they should perform, just the question of does this PCB faithfully implement the schematic is really hard. And it's really hard because you fundamentally have to solve the full Maxwell equations, right? All the wave dynamics of the Maxwell equations. And you have to answer all of the possible things that could go wrong. Right. So if you have even a simple board with 1,000 pins, or 1,000 traces connecting those pins, in fact, every single one of those is emitting some amount of electromagnetic radiation that couples into every other single one. Right. And so you have to be aware of that, and you have to determine whether that is too much or within spec, basically. And so there are kind of industry standard rules that you follow that are basically approximations that you can use to kind of usually be okay. And then in some cases, people will do some amount of simulation to try to determine this. But in general, it's actually a very difficult question of like actually making completely sure that you've thought of everything and then you've tested every possible scenario and before you go and fab the board.
And this ends up in a pretty slow iteration cycle, right? I know that you've talked previously about how for your own simulation and what you've been doing with Quilter, you had built out a full, Maxwell equation solver. And it turns out that this is pretty slow to do. And so you need to deal with approximations. And so there's this tough balance of how well can one approximate what we know about how safe this board is going to be, what's going to happen, versus actually trying to give people some sense of how well it's going to work and letting them kind of move on with their lives or onto the next iteration.
Yeah, 100%. I think for if you're running a simulation once and you know exactly what question to ask, it's not unreasonable, right? So the sim, like we didn't have to invent our own simulation. There's plenty of commercial and open source solvers out there that we can use, and the one that we built in originally was an open source solver. And it can do, like, if you know exactly what question to ask, you know that a certain trace is going to emit power, a certain trace is going to potentially be interfered with, and you ask that exact question of the simulation, a single GPU can knock that out in 10, 20, 30, 40 minutes, depending on the size of the board. So that is not unreasonable. But when you're considering exploring the entire design space of all the different ways you could have arranged that board, right? If you're designing that board, and you're also considering, not just one such query, but thousands of such queries, then it becomes prohibitive. So definitely, that's something our team is currently investing in. Is how do we take approximations along the way? How do we? They could be analytic approximations. They could be maybe 2D or 2.5D solvers, and eventually we hope that neural networks can make some of those approximations for us, or even just suggest boards that are unlikely to have those issues in the first place.
I want to come to the question of exploring the entire design space maybe broadly in a second, but one way in which I think this kind of manifested for you was this point about octilinear traces, which I think eventually became a part of what Quilter is doing. And it seemed like there was some back and forth because on one hand, from where you were coming from, you have said that if you reason in a first principles manner, then octilinear tracing isn't necessarily a constraint we need, and in fact, things could potentially be better in another way. And I think you've kind of likened this into the way in which AI systems will give very creative solutions, for example, in games like Go. And so that's really interesting. It does sound like you eventually added this as a feature of your product. And I'm wondering what that back and forth looked like and what you pushed you to eventually make that decision of, okay, we're going to do octilinear traces.
Yeah, it's a good question. I think the final thing that kind of pushed us into it was I definitely resisted it for a long time because it didn't make sense to me from first principles, right? Like if you're not designing the board and you're looking for the best signal integrity on all your traces, then smooth paths make sense. And when you look at high frequency designs, that is what people do. But there were two things that were pulling us away from that. Number one is just like the intense gut reaction of any electrical engineer that looked at those boards, right? I think we obviously speak with users and customers all the time, and we categorize all the feedback, and we sort it and classify it, and like this was by far, by like a factor of 5, the thing that everybody pushed back on, and like rather than go and explain to everyone that hey, it's okay, like we should just eliminate that as a concern. I will give one real reason that finally convinced me, which is that we are not capable at this point of like designing any single board with such confidence that nobody should review it, right? That's certainly the goal, but we're not nearly there. And so it's realistic that people will open up the design files we produce and they will modify them. And the fact is that all of the CAD software out there, Altium, KiCad, Cadence, so on and so forth, are really well suited for allowing you to manipulate octilinear traces. Like when you grab an octilinear trace and you move it around the screen, everything responds very nicely and rearranges. Whereas if you try to do that with smooth traces, it kind of chokes. And so that's a very real feature, right? The fact that our users still going to modify the board and they should have a convenient time doing so means it's important. But I hope one day we can cut it back out.
So it's really a paradigm dependent thing, right? It seems like when maybe you were imagining forward to the point, of course, as you've said, you're not quite there yet, but if we project forward to the hopeful eventual version of Quilter, where it's good enough that it can design boards and doesn't necessarily need human review, then yes, who cares about the gut reaction somebody's going to have to the traces? But in the world we're living in right now, it seems like in addition to that good reason you pointed out, people are going to have to use this other software. Engineers are going to have to stare at this. And so maybe there's a timeline on which A, you can move away from this sort of tracing, and then B, maybe you can train people to have a little bit less of this super awful visceral reaction to it, perhaps.
Yeah, I think it'll ultimately come with data, right? Like, and we're serving engineers. Engineers are driven by data and by physics at the end of the day. And so I think that what will eventually happen is we'll just present boards that perform better, right? Like we'll make a board that's smaller or faster or cheaper or something like that as a consequence. And then when you go and you force us to use octilinear traces, you won't be able to accomplish the same metrics. And that will be the ultimate kind of deciding factor at some point.
So I'm not a super experienced engineer in this domain. I haven't built a bunch of PCBs, but I've built some very, very basic boards for things like computer engineering classes. And I'm wondering, maybe going back to the broader point of exploring the entire design space of what a PCB could look like and how you would build that. How do you think about that question?
Yeah, it's a really good question. So, I mean, in general, this is a drastically exponential problem, right? Like it's practically completely impossible to go and actually look at every single way it could be arranged. So the way that we kind of approach it is to try to search reasonably distinct options. So at the highest levels, things that engineers decide early on in the process of a circuit board design are things like, what is the outline of this board? Maybe it's driven by mechanical constraints. Maybe you're just trying to make it as small as possible. Maybe you're having a back and forth with the mechanical team of how much space you're allowed. It's also things like the placement of your connectors, the stack up. So that's kind of how many layers you're going to have, what those layers do. And those things get locked in usually pretty early. And then, so maybe if you have a 4-week kind of layout process, you'll lock those in the first week. And then you're kind of stuck with those decisions through the end of the design phase. And if we have an instant kind of compiler that can just take the schematic and output this thing, that means there's no reason to kind of be locked into those choices. So, where a human expects to make just a single layout and say, okay, I hope this is it. Quilter has no reason not to make hundreds or even thousands and just to really explore that boundary. So at the simplest sense of exploring the design space, we can explore things like, can we make this board smaller for you? Can we make it with 2 layers versus 6 layers versus 10 layers? And what does that mean? Ultimately, that ties into cost and performance. And so we can kind of allow you to eventually walk this trade between, what do I have to do to make it kind of cheap and be delivered very, very soon versus, maybe more expensive, but more high performing. And that's kind of what Quilter is intended to enable. There's also the details of like the specifics of the implementation, right? So we, under the hood, explore millions of different placements for components and thousands of different routing topologies, all of which eventually have trade-offs. And that's less of what engineers typically think about at the beginning, but it's still important in terms of trading off, like, how small of a trace you can get away with, and what kind of electromagnetic characteristics you're going to have.
I have a bunch of questions around that, but maybe a first one is an important feature of your product and when you are trying to build out a board for somebody is, and especially as you iterate on your own product and improve it, is the set of benchmarks you're using to measure how good it is. And one of the key components, of course, is manufacturability, and then completion. Did you actually finish up the design? But it seems like that isn't all people seem to care about. And I recall, I think on your blog, for example, it was either on your blog or somewhere else, there were some comments on aesthetics. And so that ended up being a pretty important feature for you. So I'm wondering about, of course, certain things are going to be more and less easy to measure. But when you think about benchmarking your product, are there things that you think are really core and important to people right now that are just missing from what you're able to measure at the moment? And what does the best version of a benchmark you think you could feasibly implement look like for you?
Mm. So first question is, do we have things missing that are important to people? Unequivocally, 100% yes. Quite a few. So the way that I think about what the ultimate benchmark should be is, there's kind of like basically two elements to it, right? The first element is this board actually going to work? And the second is, how expensive is it, right? At the most global sense, those are the two things that people care about. So expense is relatively straightforward to measure, but is it going to work is not, right? So if you haven't placed all the components and you haven't routed everything, okay, that's really, really obvious. It's not going to work. That's a baseline. But what gets more interesting is when you start to consider all of the physics that's happening on the board, right? So in the limit of low current, low voltage, low speed, or like low frequency, if you've connected everything, you're done, right? Like you can basically ignore everything and it's going to be fine, right? So even if you're designing something like an Arduino Uno, or some basic circuitry, it's going to work. It's going to be okay. That breaks down when you raise away from those limits, right? When you have non-negligible current, non-negligible frequencies, non-negligible voltages, you start to worry about things that could go wrong. So, like, fundamentally, the most important thing about a PCB is that its job is to faithfully recreate the intent of the schematic, right? The schematic assumes, a perfect world where all traces are isolated, they're, infinitely conductive, and, so on and so forth. But in the PCB, that's not the case. So you have to enumerate all of those concerns and verify that all of those, these are sometimes called parasitic effects, are below the threshold at which they kind of stop the circuit from working. So for us, we're diving into those domains, right? So we've done a bit of work on carrying current, right? So Quilter is kind of open about being able to support anything up to about 4 amps. And that consideration is pretty simple, right? You can do a very straightforward analytic calculation to determine, how thick a trace needs to be and also how tall it needs to be in order to not heat up above 10 C or 20 C above ambient and still support that current. That's pretty straightforward. The next thing we're starting to get into, and this is something that we'll ship fairly soon, is higher speed signals and things like differential pairs. So that's where you start to not be able to ignore the wave dynamics that's happening. Like you have to account for effectively the speed of light in the trace. You have to account for the fact that you have two signals that are traveling from point A to point B at the same time, and they have to arrive at the same time to like cancel each other out correctly. You have to account for the fact that those two traces are creating a magnetic field between them, and so you want to minimize that and its impact on everything else, so on and so on and so forth. So the way that we think about building up these benchmarks is kind of from the electrical engineer's perspective, right? So what we'll do is, hey, right now, if you come to us and you input something with up to 4 amps and you actually specify all of those currents throughout the board, we'll handle that fine. Next, if you come to us, in a month or two or whenever we ship this feature, and you tell us, hey, I've got a USB connector here, that's going to require differential pairs. Therefore, we will then make a good conclusion about what to do with that, and then we will be able to verify it and kind of guarantee that it's going to work. And we have to go through the entire landscape of all of the things that could be happening on a board to eventually cover all of the cases.
When you're building the system, one component of it, I suppose, is you're trying to figure out how can neural networks also help solve this problem. And I guess the RL paradigm is interesting because it feels like it can be quite well suited to this problem. And at the same time, you do have to be really careful in your domain about ensuring that your system doesn't do things that are very weird, that are kind of like wireheading or shortcut learning. And so you can imagine asking your system to build a PCB that implements a certain functionality, and then maybe it takes advantage of parasitics or something like this and is not at all what a human would do. And so I'm wondering if you can talk a little bit about both how you're thinking about building a system like this, but then also guarding against those sorts of things that we might not want.
Totally. Let me take a quick tangent for a second.
Sure.
That idea of a system that took advantage of parasitics, that didn't happen to us, but has happened. There was a really cool paper that somebody published on configuring an FPGA with a genetic algorithm before the neural network days. And they were basically saying, hey, bits in, I want certain bits out. Please come up with the configuration between. And what they realized when they kind of inspected the configuration came up with was that it was actually taking account parasitics and using parasitics as part of the signal chain rather than like the logical intent of the FPGA. Fascinating, absolutely fascinating. But exactly, so it's a very, very, very possible thing to happen. So the question is, how do we guard against that and avoid that? So one of the convenient things in our domain is that we are posing this as a reinforcement learning problem, and for us, we have the power to control not just the agent and the score, but also the game itself. So what we can do is we can simply make only allow the agent to use moves that basically avoid scenarios like that, right? So in our game, like, you have to connect from pin A to pin B with a solid trace. Like, you can't just stop halfway through, leave some gap, and use parasitics to couple and connect that way today, right? So it's impossible for the agent to propose a solution like that. Eventually, I'd love to loosen those constraints, right? In the 10 or the 100-year future, I think we should propose arbitrary copper and allow it to find these kind of weird electromagnetic anomalies. Well, not anomalies, it's just physics that can take advantage of those things and make better boards. But for today, by building the game, we can prevent that from happening.
How do you think about some of, I suppose, the more detail-oriented components of this, and not just connecting one component to another component, but the concept of appropriate track widths, for example? I think that was something that came up and I know you talked about how there was a pretty simple bug in your program, but I remember Tom Fleet, and I suppose a lot of the grumpy hardware engineers on Twitter were looking at an initial design of yours and were like, there's a lot of things wrong with this. And so I guess I'd love for you to comment on how you think about some of those more detailed aspects of this and how you're kind of integrating that into your system and some of those difficulties.
Yeah, I mean, I think it comes down to, in that case, yeah, we just simply had a bug where we had specified that was a high current thing, and it was just simply disconnected from the back end. So, whoops. But more importantly, like, for a while, Quilter is going to have certain features that it supports and certain features that it doesn't. Right. So today, like, if you log into Quilter right now at this instant and you ask it to do, a 3-4 amp trace, then it will correctly calculate the trace width and it'll use the correct trace width. And that's fine. I'm very confident that works okay. But if you're hoping for it to correctly do a differential pair, right, to correctly hook up a USB, it won't do that. Like, you don't have the ability to even tell Quilter that signal is a differential pair. It's a USB. You have to take special precautions with it. So I think what we have to do is be very, very clear with what are the fundamental features that we can support and consider, and what are the ones that we can't. right? So there's a part of our user experience that we kind of loosely label constraints, where we communicate that with the user. So I think what maybe people were hoping for from Quilter is that it like already magically knows everything, that it like already went and read all the data sheets and figured out that things are high speed and RF and need characters to pieces. But that's just not the case. Like, we're gonna have to go through these things one at a time. Introduce some automation to read them automatically from data sheets, but still allow the user to verify that we made the right conclusions, to override them. And then at the end of the day, the user will see exactly all of the physics that we are accounting for, and by omission, anything that we're not accounting for.
Are there any particular features that strike you as just things that maybe Quilter won't be able to incorporate or are going to be especially hard? Or do you think in the fullness of time, assuming that you kind of have the funding and enough people and everything like that, that you're going to be able to get your hands around everything important?
As far as the functionality of the board, I'm completely confident we'll solve everything eventually. I don't think it'll be in the next 6 months, but in the 10, 20, 30-year future, like, definitely. And I mean, the cool thing will be that hopefully, electronics design and PCB design progress, and Quilter catches up to the cutting edge of it, and maybe helps push some of those boundaries. And then people will find ways of doing things that we can't currently handle, and then we'll innovate. And I hope that never stops. The one thing that I am a bit concerned about, though, is actually just pure aesthetics, right? So, especially today, electrical engineers, I mean, rightfully so, take a lot of pride in their board designs, right? If this is something that you train to do, you do it 100% of your day. I mean, people will take their boards and they will put them in frames and like hang them on their walls and be proud to show them to other people. And a lot of that really is just beauty, right? Like, of course, the beauty kind of was, I think, motivated by making sure that the board was going to work. But there's also some amount of like, is it readable by another human? Is it kind of easy to understand for somebody who hasn't seen it before? But I mean, also just purely, is it like aesthetically pleasing? Is it symmetric?
Yeah, it feels like some people look at it as a kind of art.
100%, 100%. And it can be. Like, if you look at a beautifully designed circuit board, it is actually very pretty. And that's where I don't know exactly how we'll approach that. Like, trying to encode that in math seems like not the best way. Maybe eventually we generate so many designs and people upvote and downvote on them, that we start to pick up the patterns of what people find pretty. Maybe we just make the argument that it need not matter, right? In most cases, the PCB is not facing your consumer. And so why does it matter what it looks like? There's counterexamples to that, right? So, like for NVIDIA, their buyer is going to look at the 4090 and they're going to appreciate it as they install it in their machine, right? And somebody's going to do a teardown of it. So it's important to them that the top layer and the bottom layer of that board look pleasing and look beautiful. Anyway, that is an area where I don't see an exact path for how to get there. I'm sure it's solvable, but like, it's more interesting to me. But I think that everything that has to do with just like physics, I think is solvable.
Yeah, and maybe that last comment, a way this fits in, is looking at the question of how a tool like Quilter in its kind of platonic form fits in alongside with and changes the jobs and the ways in which people look at and think about PCBs, the engineers who are going to use a tool like this. Because I can see one version of this where Quilter is able to take care of all of the, I suppose, I have a PCB and needs to get a job done. And so I have a tool that can help me get that job done. And then maybe people are still building PCBs on the side, excuse me, as something like an artistic endeavor, and totally not for, not with the sorts of constraints of, oh, this is an object that has to do a thing. But I'm curious how you think about that whole interaction.
Yeah, I mean, I think that both of those will be prevalent, right? And let's acknowledge that there may be cases where you still need something very, very, very special that Quilter hasn't thought of, right? Like today, I don't know what fraction, 99.999% of code is compiled, and we don't review the assembly going into the processor. But like, there are cases where you do. there are cases where you're questioning whether the compiler did a good job in putting the thing together, or you want to have some sort of safety guarantee or something like that, and you might review it. So I think that will remain. I think certainly people doing it as a kind of art will definitely remain. I mean, people. One of the cool things in this industry is people still build like retro computers for fun, right? Like computers that emulate the processor like the 70s and 80s, and it's a great exercise to just like understand how computers work. And I think that hopefully that will remain. But I think like there will be another change too, right? Like I think that because it's so laborious today, we can't explore as many options. Like, right, I fundamentally think that every PCB out there, I mean, including the ones that get produced in the millions, are over designed. Right? They're too big, they're too expensive, they have too many layers, because you are so afraid of making a mistake that will prevent that board from working, that you make a bunch of conservative assumptions on top of each other to prevent that from happening. And so, like, when you have a tool that instantly generates boards and can kind of approximate physics better than humans can, you could just design better boards, right? Like, not just like, here's a board I know can get this job done, but what's the limit of like the best board that I could design for this kind of application?
You brought up the compiler analogy again, and that was something that, as I was going through all the information available about Quilter, I was kind of curious how seriously you took that analogy. And it seems like even from the perspective of the way in which you've structured your software stack, there are lots of analogies in there. There's a kind of modularity going on. You've got this placement section, you've got the routing section, the post-processing section. And I remember you had a blog post about how you'd solved this rate limiting step by rewriting the localized routing part of your system in C++. I'm curious how you think about maybe the analogies and structure there, if there are any places where you see disanalogies, and just how you think about the compiler analogy in general.
Yeah, so I primarily take the compiler analogy to heart in the product experience itself, right? Of like, compilers used to not exist. People used to have to actually write in, each bit into the register of a processor. And over time, when they were first created, they weren't trusted, they were inefficient, much worse than humans. And over time, they're inevitable. And so I think of like the experience of what it should feel like to use Quilter as very strongly guided by what it's like to use a compiler. We literally built in what we think of as a linter, right? So people frequently give us kind of incoherent inputs. A lot of people, when they first come to Quilter, they upload a fully finished design because they're probably trying to just compare us to what they did by hand. And didn't think about the fact that, like, if the board is complete, there's nothing for us to do. And so we have these kind of linting stages that detect issues like that and many others. Under the hood, I don't think that analogy is nearly as strong, right? Like, I think that in the landscape of a real compiler, and by no means do I know much at all about real compilers, but my understanding is that, like, you have a perfect representation of your logic that's information complete in your input, right? In your language that gets turned into tokens that can get processed into a tree of execution that you can then optimize. And that's just like not quite the case in PCB, right? Like, your schematic is not information complete. You have to factor in what the chips are doing in between. You have to factor in the physics. And it's not also clear to me that, like, the same kind of structuring of building out a execution tree and being able to kind of collapse it and massage it and turn it into a set of other execution commands applies here. So yeah, I think we take it most seriously at the product experience rather than the kind of technical level.
Yeah, I was kind of curious because the space I currently work in is ML compilers, and so there are some similarities there I noticed, and perhaps it's not quite at the exponential level that you talk about, but there are places in which, say, for a neural network, the graphical structure of it is going to impose certain constraints on what your compiled artifact looks like. But there are ways that you can play around with and think about, for example, the live range of certain tensors in your graph and things like this. So there are ways in which different frameworks are going to hand off pretty different graphs for the same neural network to you. But it does seem like there are some kind of interesting analogies there. And I suppose, as you said, though, it's not quite perfect.
And for what it's worth, like, I've been actively trying to find people who are experts in compilers to learn from on this, both history and implementation. So if anybody wants to chat about that, I'm all ears.
Yeah, I'm actually really curious about how you think about this aspect of you're kind of working across a set of areas that, again, there are some analogies here, but then there's pretty different spaces of engineers who are experts in the different areas that you're thinking about. So on the one hand, you have, you want to have people who know a lot about PCBs, people who know a lot about reinforcement learning, probably people who know something about compilers. And I'm wondering how you think about this aspect of like gluing those social worlds that your product seems to span.
Yeah, that is the $1 billion question. I think I think that's really really important. I mean, I think fundamentally, like, why doesn't this automation exist? Like, you look at software and how many tools are created in software every day, and I think that fundamentally comes from the fact that, as a software engineer, you do something repetitive, you get tired of it, you automate it, and then you're like, wait, other people have this problem, and then you share it, right? You make a GitHub or you start a company or whatever else, and like, that's wonderful, and then people can build on top of those abstractions, and it can kind of run away from itself. The thing is like, as a PCB designer, as an electrical engineer, you're usually not a software engineer. So when you don't like the software that you're working with, you don't have the kind of tools to go and modify it. They're also usually closed source tools that you can't really poke at and play with, and so on and so forth. So what we have to do is exactly what you said, right? Bring people together from totally different domains. So most of the people that write software at Quilter, like, are not PCB experts, and then the PCB experts that we do have on the team are not experts in writing software, and they have to find a language and a bridge. I don't know that I have a magic bullet for it, but I think, like, a bunch of smart people working in proximity with a lot of empathy for each other, learning from each other, and being curious from each other overcomes that. I think that's really the key. It's just smart, curious people in the same room who want to learn from each other.
One question that's been lingering in my mind, and maybe this is a bit of a left turn from where we are right now, is something we'd spoken about earlier, the theme of first principles thinking. And we talked about it in the context of octilinear traces earlier, but it seems like there are ways in which, when you're developing an AI based solution for a system like this, the first principles thinking kind of comes in almost automatically, because without appropriate constraints, an AI system is going to develop solutions that look really weird to us humans. And at the same time, though, you do have lots of engineers out there who have been designing PCBs for a long, long, long time. And so there's this aspect of the process knowledge that these people collectively and individually have, just as a fact of having done this so much. And yes, there are ways in which they can be mistaken about things, but it's really powerful to have an engineer there who can just kind of stare at a PCB and be able to infer some things about how this is going to work, how this is not going to work. And so I'm wondering how you think about perhaps that. I don't know if I would describe it as a tension, but there is this, on the one hand, thinking about everything from first principles, and then on the other hand, a lot of wisdom and expertise that has been accumulated over time. And so in the context of building a product like Quilter, I wonder how you think about those two things.
Yeah, that's a really good question. So I take a lot of inspiration from the journey that Tesla walked with autopilot. So if you look back into, like, the 2016, 2017 days of autopilot, you had this code base that was, to my understanding, a relatively simple neural net that just takes a 2D image and segments it, and then, like, millions of lines of C++ that turn that into, like, what is the world we're in, how do we plan in it, how do we drive, and so on and so forth. And the analogy or kind of maybe the procedure that Andrej Karpathy talked about that I really love is, like, neural networks eventually ate the C++. So I think about this in that perspective, right? That, like, when you think about an electrical engineer's wisdom, what they're doing is they're saying, hey, there's maybe all of these infinitely many ways to satisfy the core problem, the first principles problem of, like, I don't know, avoiding crosstalk, right? But instead of exploring all the possible ways that could happen, let's take a slightly smaller space where we're very confident it will happen, like a simple heuristic rule we can follow. So I'll give one example for this. If you have two traces next to each other, and one of them is running current, that current can propagate via an electromagnetic field to the other trace. And that's a problem. And in general, to solve that problem, you want to run a full wave simulation. But that's too expensive and too slow. So what electrical engineers do is they have a relatively simple rule that they follow called basically 3 widths. Or sometimes people go even further and do 5 widths. And the idea is that if the separation between your two traces is 3 times the height between the trace and your ground plane, then the field should be small enough, and therefore you're good. Right. So from first principles, maybe you could have gotten away with 2 widths. Maybe you could have even gotten away with 1 width, but 3 width is definitely safe. So I actually think of us building Quilter as starting with a lot of those first principle wisdoms, right? We don't need to rederive the 3 widths rule. We don't need to rederive the fact that differential pairs have to be close together. We don't have to rederive the thickness of a trace that is required to carry a high current. We can just start with that. We can just hard code it and just say, Quilter, do this when you see the situation. But over time, as we introduce more and more power and flexibility and simulation to the neural networks, we can eventually release those constraints and maybe cut away more margin. So that's kind of how I think about it.
It seems like it's going to be very important that at the point you're able to shift from that ingrained knowledge to something that's a bit more first principles based, that you have lots of data there, because I can see how in this case of that simple rule and the widths, that you also actively might want to have something that is slightly more conservative in terms of distance, because yes, maybe based off of simulation, we know something about the electromagnetic fields, but it's possible that things could fluctuate somewhat when we actually have things out there, especially if in simulation you're not using like the full Maxwell equation solver or something. So it seems like that aspect of gathering data and kind of seeing how things work out in the real world is pretty important too.
I certainly think so. And for that reason, like we internally build quite a few boards. We have a bunch of boards that we've built on our blog, and we're going to build many, many more. And we're very interested when our users build boards to kind of learn about how it went and so on and so forth. But I think that the vast majority of these problems are computable, right? Like if you double check your full result with a full wave simulation, and you've kind of make sure that you've set it up right, and you've made sure that you've understood all of the tolerances of the manufacturer and all the things that can kind of be off in all the different signal types and chips and everything like that, you should be able to compute the answer. And really, we would probably catch these things only in the most obscure, most crazy kind of places. But I mean, we haven't committed to anything like this. This would be a long time away, but like, I'd love for us to actually run like a EMI lab or something like that, right? Where we are responsible not just for making the design of the board, but then after a manufacturer manufactures it, like we take it in, we test it, we actually maybe even do the FCC style qualification that it passes, emissions and whatnot. And then if we see a mistake, then it's on us. Like we screwed it up, and then we redo it. Not something we're thinking about yet, but it would be very interesting to do something like that.
Can you tell me about some of that dog fooding you did on your own product, the boards you built, and then maybe if that revealed to you, I suppose, any features, issues that you just hadn't picked up on earlier?
Yeah, good question. We've built internally a number of boards. Whenever we built them, we were pretty confident that they were going to work. Otherwise, we wouldn't have spent the time to actually manufacture them. I think in the with the first couple of designs that we did, like we basically just had a Python script that was the compiler and none of the UX. And so that was a lot of that was just learning about like how to set up a run like this, how to make a user experience that does this, things of that nature. Um, there's also just, and I kind of knew this before doing Quilter, but it kind of reassured me again that like even once you have the design, like your journey's not over, right? Like you still have to send the board to a fabricator. You still have to assemble it. When you assemble it, there's still issues with like, oh, I soldered it, but I accidentally bridged 2 pins and it's not working. And I'm questioning why until I look really, really closely and realized I screwed up during assembly. Right. And so at the end, like every board that we've built so far worked. Like I think the kind of most complex or interesting board we built was a computer vision board that could, look at a camera, pipe that to an STM32, do some onboard processing, even run an onboard neural network, output to a screen, and like we did something silly with it. We put a mustache on a human face because shout out to Silicon Valley. But but like in the process of getting it to work, like we were questioning our own layout. We're like, oh man, did we screw this up? Like, why is this not working at first? And we figured out, oh, like solder bridge, or I held the heat gun too long to a component and burned it out, and so on and so forth. And we finally did the assembly right. It was like, okay, actually it is working, it's okay. And so I personally gained a lot, even a lot more empathy for like the anxiety that an engineer has when they commit to manufacturing the board. Like your design is kind of so locked in, and when you get it back and it isn't just immediately working, which is never the case, that fear of like, oh man, did I make a mistake that I can't come back from, that I have to go and redesign the board for, or am I just making a mistake in the assembly or how I program the chip or something like that? And so I think it's going to be really important for us to provide a lot more proof than is even standard for a typical designer, for why we are confident that this board will work.
I'm wondering how we talked about this kind of briefly, but I'm wondering if you could comment a little bit on, especially for people who maybe aren't familiar with the automation that PCB designers already use and the space of what that looks like. You talked earlier when you were discussing your internship at SpaceX that automation had failed you. I'm wondering if you could speak a little bit to why that was, and then the sort of automation people are using now and how you think about Quilter in that landscape.
Yeah, totally. So the biggest automation that is present in most ECAD tools are these sets of tools called autorouters. So in most cases, the idea is that you're still kind of on your own to place the components on the board, to conclude what your stack up should be, to set the design rules, to figure out what manufacturer you're going to use and what that implies for tolerances, and configure all of that. But at the very least, one of the laborious parts of designing the board is just connecting all the dots. And that, an algorithm should be able to connect that. And that's what autorouters have been attempting for actually since the early 60s. Like the first autorouter I saw a paper for was from about 1961. So they even predated to some extent EDA tools, never mind full automation. So where do those systems fail? Practically speaking, if you go up to most electrical engineers and ask them what they think of autorouters, they basically laugh at you. In the vast majority of cases, nobody uses them. Like at best, I've only ever heard of two kind of reasonable use cases for it that people take seriously. One is like, I did all of the hard parts of the board myself, and I have a bunch of signals that I'm confident are low speed, low power, can't screw them up, and I let the autorouter take a shot at it. That's one use case. The other use case is I place my board, I run the autorouter. If the autorouter was able to solve more than 90% of the board, then I know my placement is reasonable. I delete all the traces and then proceed to redo them myself. That's kind of really the status quo, right? Like if you look at a professional design, Apple motherboard or video card or SpaceX flight computer, those are all hand-drawn traces. So why do they fail? They fail for two reasons. The first and most basic reason is that for a board of any reasonable complexity, the autorouter quite simply just does not finish the job. Like maybe the problem here is that this routing, it's an exponentially difficult maze, right? So routing your first trace is just, hey, I have a start point, an end point, some obstacles, maze problem, right? CS1A, not too hard. But the difficulty arises in that your solution to that maze becomes an obstacle for your next maze. So by the time that you've done it 10,000 times, how did you make sure that the 10,001st trace still has room left over to find a solution? That problem is obviously exponentially difficult, and autorouters don't solve it, right? They'll get to 90%, then they'll stop. And as a user, you kind of see why it stopped, right? You see that there's no way to route the other 10, so you start deleting stuff, shoving stuff around, and it's like half the work to finish the last 10%, right? And so usually people find that really frustrating and just delete all the traces and start over. That's problem number one, right? Like if the compiler didn't compile all the code, you can't run the code. And it's very, very painful to then manually compile the section it didn't work with and make it work with what it did compile, right? The second part is that autorouters just don't think about physics. So they put the burden back on the user to answer the question of, is the design that I'm seeing in front of me actually going to work, right? Are all of the electromagnetics going to check out? And that is a harder problem than just routing it with all those rules of thumb, like the 3-width rule and whatnot in the first place. So that, I think, is the reason that automation has failed, right? In my case, I saw it didn't finish it, and I wasn't confident with the physics, so I deleted it, never tried it again. And most electrical engineers I talked to, that's roughly the experience they went through.
One thing you talked about too was the failure in completion, especially when you're getting to larger and larger boards. And I think one thing you've mentioned about Quilter right now is that the system is pretty limited in the size of boards it can deal with. And so your recommendations for people who want to use the product are with boards specifically of a certain size. And I'm wondering if you can talk about where that is now and then maybe the challenges you see ahead for solving and building your system up to the point where hopefully it can cope with larger and larger boards.
Yeah, definitely. So I think that there's kind of maybe a few different challenges, right? So when you have a bigger board, you can think of it as presenting a kind of like a much larger tree search that you have to accomplish, right? With every trace that you're routing and every component that you're placing, you have many branches of options, and once you've taken a choice, then you have 1,000 more traces to place, each of which has dozens of options as you do so, and so it's a large tree. So how do you solve a kind of tree search problem? One thing is just make it as fast as possible to search across that tree, just so that you can go to more places, right? And that's a lot of what we're investing in now, right? So the article or the blog that we published about the local routing module being much, much, much faster, and all of the work that's proceeding now, that's going to make the whole pipeline much faster, is sorted around that, right? Like, let us have 10x, 100x, 1000x the ability to search the tree. Alone, that's not sufficient, right? What you need next is you need some ability to prune the tree, right? You want to limit the breadth and the depth of search, frankly, in looking for the solution.
Mhm.
That's a lot of where RL itself comes in, right? So even with basic policies that point you at good choices within that tree search, you can focus that search much more significantly.
Another thing that I wanted to get you to comment on with this was I suppose in the ways you've spoken about the product and as you're building it out, you are really trying to integrate with the community you're targeting. And so you have forums and things like this to get feedback. And in the way you've been talking to me, it's pretty obvious that you take that feedback very seriously and you want this kind of ongoing conversation with the engineers who are going to use your product. And so I'm wondering how you think about kind of that strategy, but then also the fact that maybe there are going to be many engineers out there who have the kinds of experiences with auto routers that you talked about, and maybe are going to come at a product like this with some kind of skepticism.
Yeah, I mean that's certainly going to be the case. I think that in our industry, of course, lots of people have had bad experiences with auto routers, and that doesn't exactly put automation in a good light. I think we also have the challenge of that every other kind of AI automation company is facing around people generally figuring out where should you use it, how much you can trust it, is it going to come from my job, like those kinds of questions. So I think about a couple of things here. I mean, so number one, most importantly, the burden of proof is on us to demonstrate why you should pay attention to this and why it's going to be interesting and why this can actually help you, right? So, like we are going to, over the months and years, produce more and more and more sophisticated boards that were done with complete automation. Um, eventually those boards will be more sophisticated than most boards that engineers design on a daily basis. And so at that point, you'll have to ask yourself, like, is it really wise for me to spend the next month doing this and being a critical path bottleneck for my company and my teammates when I could just, run Quilter, configure it correctly, and have a board on my desk in 2 days? So I think that like nothing substitutes the kind of proof in the pudding, and it's the burden's on us to demonstrate that over time. But I think the other thing that I found really exciting, and especially from announcing our most recent fundraise and kind of being a lot more public about Quilter, is that a lot of people are ready. Like, there are a lot of people who for sure don't see this working out, and think it's going to be too difficult, but there's a lot of people who are saying, man, I really can't believe this hasn't been done. I know it's going to be hard, but you guys, like, please do it. And I see so much of that, right? Like, we have people signing up for Quilter every day, and so frequently I get messages on LinkedIn or by email or in the sign up forms, whatever, that are like, power to you guys. Like, I believe in what you're doing. Let me know how I can help. When I email a user, they always respond. They're happy to take the call. I think there's enough of a critical mass of people who want this to exist for us to have plenty of good feedback to work with.
I have a question for you about how you maybe personally experience a little bit of this. We discussed earlier the Tom Fleet comment, and you rightly pointed out that where some of the commentary there came from was this gap between what you thought the product you were putting out was, and then the expectation other engineers had about where this product should be. And I think maybe one of the things that Tom was pointing out too was this concern he had specifically over the claim that Quilter was taking physics into account. And you mentioned again that this was attributed to a bug, but I think he was also saying something like, oh, maybe that claim is false. And as many people know, being a founder is very hard for all sorts of reasons. So I'm just wondering how you personally kind of experience that aspect of there being this kind of hard, possibly grumpy market to tap. A lot of people who also want what you were trying to deliver to them, but managing those expectations and sort of putting out that thing you want to exist in the world into the world, and managing the gap between what you think it is and what other people think it is.
Yeah, that's a really good question. And I mean, speaking to any other founders out there, like it's gonna happen. It's emotionally difficult, right? Like you're putting your care and your love into this thing, and not everybody's gonna see it for good. Not everybody's gonna see it in the optimistic lens that you see it in, and of course that hurts. It's not a pleasant feeling by any means. But the way that I kind of think about it, and that I'm okay with it, is that, and I've learned this more from from mentors, from investors who've seen many companies to go through these cycles, is that the worst thing that can happen when you put out your product is that you put it out there and nobody cares. Like it's just crickets. Whereas when you get a bunch of people who are super excited and a bunch of people who are skeptical, that's actually a good thing. Like you've struck a nerve, right? You are spawning a discussion that is worthy of being had. Um, it's not like you're ever going to make everybody happy, but the fact that you're doing something that people care about, something that matters, is a good thing. Like that's a signal that you're going in the right direction. So, and just frankly, like what I do personally is I listen to a lot of other founders, on podcasts like this that have gone much further on the journey than I have. And there's probably not a single founder who was successful who didn't go through a whole bunch of people not believing them, not believing in them, through a whole bunch of crucible moments and whatnot. I mean, literally, Sequoia has a podcast called Crucible Moments about this exact topic. It's not always about how products are perceived, but it's about all sorts of difficulties you're going to have. So I kind of view it as a necessary and important part of the journey.
Are you open to sharing maybe just a little bit more about what that looks like for you when it comes to trying to keep the resources and the support around you and kind of maintaining the strength to keep doing the difficult thing that you're doing in the face of a lot of that?
Yeah, 100%. Always happy to. And for what it's worth, like one of my favorite things about doing this job of being a founder is speaking with other founders and like having, supporting them and them supporting me in this way. I think it's a wonderful thing and a wonderful community. How do I deal with it? I do a few things. So first things first, I, kind of have kind of an introverted background, but I've pushed myself a lot on changing that, on being vulnerable and open with people. And so when I have an emotion like that, I challenge myself to actually tell the people around me rather than bottling it up and pretending like it's not there. I think that's really important. And nobody's ever kind of punished me for it. To the contrary, everybody's always supported me, and that's great. Another thing that I found really helpful is getting really into exercise. And in particular, I've gotten into like combat sports, mixed martial arts and Krav Maga and everything. And a lot of that has to do with staying calm in a high pressure situation, right? Like you're getting punched, you're getting kicked, you're exhausted. How do you calm your breath and think rationally and take the next step and, fight your way through the problem? I find that very helpful. I found, meditation very helpful. This idea of like noticing thoughts as they bubble up in your head and recognizing them for what they are rather than living inside of them. Very helpful. And just like taking time away from the job, right? Like, a lot of times it's when I, took a weekend and I'm spending time with my wife and my kids, or even just getting bored, not working, that I get re-inspired, right? Like at the end of the day, the thing that I wake up, no matter how hard it gets, that I get inspired by is like picturing this world that I think is inevitable, where this problem and many others like it are solved, and what we can create. Like what happens when a 10-year-old can just imagine an electronic circuit and boom, it appears the next day on their desk, the way that people can with code today. Like that pull, that vision trumps everything. And so as long as I can get back to picturing that, everything else doesn't matter.
Does being on this journey at the point you are feel does it feel anything like what you thought it was going to feel like when you first set out on it?
I think so. I think by the time I started a company, watching watching what SpaceX had to go through, I joined fairly late in that journey, but I met a lot of the folks who were there in the early days. Like they walked away with battle scars. And so I was fully aware that like you don't build something important without the difficulty that it takes. And I was excited and ready for that. So I mean, it's different in flavor, right? Like but the intensity and the emotion is. I think I had a decent idea of what I was signing up for.
I think I just have maybe then one last question for you before I let you go. We've talked a lot about, I think, the broad pictures of what you want to achieve with Quilter and how that looks going forward. I'm wondering for you personally, just what does the world that you're in look like for you at the point where you feel like you can maybe step back from your work a little bit and say, I've done what I came here to do and I feel satisfied?
That's a good question. I mean, I think that what you described, where I feel like I can take a step back and feel satisfied, is a world where we have a electronics compiler, right? Like when the idea of even reviewing a layout is insane, the same way that the idea of reviewing the output assembly of a compiler is almost insane, unless you really, really have a good reason. At that point, I mean, hopefully, I could take a bit of a break. But after that, I'm the kind of personality that I can't imagine not going after the next problem. I don't know what that'll be. Maybe it'll be in electronics. Maybe it'll be in compute. Maybe it'll be something totally different.
Do you have any more specific theories?
Yeah. I mean, these are far, 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 far out. I don't really know. But like, one thing that bothers me within electronics is that we are very stuck to these very two-dimensional boards. But when you think from first principles, like we really should be creating like circuit volumes, not printed circuit boards, and eliminating all of the kind of box in a box that happens inside of just even a single PCB. I have no idea how to actually scale up manufacturing for an arbitrary circuit volume rather than a two-dimensional board that has very kind of known fast manufacturing processes. But like, that's something super exciting that I hope has a solution at some point in the next 100 years.
What kind of world do you think that opens up, by the way, the 3D version of this?
I think that like the nature of the kinds of circuits we could produce can change drastically, right? Like I think that you can be much more space and volume efficient. You have the potential to deal with electromagnetic isolation and enclosures and stuff like that in a much, much more kind of mass and volume efficient way. So obviously for things like space flight or aeronautics, that becomes very important. Thinking about like how to arrange electronics inside of some small product like your glasses or your earphones or something like that, where like a big planar board doesn't really fit. That could get really interesting. I mean, and eventually you're seeing a little bit of this inside of the chip domain, right? Chips are starting to be built a little bit also in the third dimension with like stacked memories and whatnot. Like that's a nice step in that direction. But like, what if you could build arbitrary logic in that direction as well, right? Like in principle, you could have a lot of memory and compute modules much closer to each other in space if they're not forced into a plane, but they're allowed to grow in 3 dimensions. And so that has potential to open up, faster compute, more memory bandwidth access and things of that nature. I think the idea is relatively obvious. The like, how the heck would we build that I don't have a solution.
Well, I hope we get to a point where you're able to think about this more, or maybe somebody listening to this will start thinking about that problem. Sergiy, thank you so much for taking the time to do this. It was really great speaking with you.
Great. Thank you, Daniel.
Thank you for listening. Thank you to my guest, Sergiy. If you like this, the best thing you can do is help spread the word and share it anywhere where you think people might find it interesting. Thanks.